This is an output of a simple host pathogen model, which shows the predicted change in grasshopper population density through time after application of a biopesticide. The pesticide is applied at the peak of the population, as indicated by these arrows here. And you will note that the peaks of the host decrease through time as the biopesticide is applied seasonally, because the grasshopper has a breeding period once in 90 days. With each application of the pesticide, the population is decreasing through time. So the temporal complexity is best reflective of the time changes. Now we go to structural complexity, and this has to do with the relationships within the ecosystem, meaning to say relationships among the components of the ecosystem. So structural complexity measures describe not only the relationships but also the organization between components of a system. This is best visualized through networks as exemplified by food web and species interaction networks. Elements of an ecosystem are called nodes, and these could be individual species or individuals, populations, habitats, or social institutions. Edges are indicative of relationships, which show the connections between elements. Now let's focus on figure 7.6, which is a food web, and the other figure, figure B, is the codified food web. You will see in the figures 12 elements or nodes. Node 12 is designated as a hub because it is connected to many other nodes. Node 12 is a high degree node because its node connection is highest. Nodes 1 to 5 are highly clustered since they are highly bundled up. Nodes 7 to 12 are highly compartmentalized, characterized by the presence of low-degree nodes. So here is the food web. These are the nodes, and the lines represent the edges or the connections between the nodes. Now the lower figure is a codified food web, so it is represented like so. Here is the high density or high degree node because it has the most number of connections to it. Let's count 1, 2, 3, 4. And this node, on the other hand, although it has 4 nodes connected to it, is one that is highly compartmentalized. There is the presence here of a low degree node. This is a high degree node, and here is a low degree node. And this is highly compartmentalized as opposed to this highly clustered node. Now let's dwell on the patterns of the structural networks. The focus here is on the linkage between the nodes. Now the pattern that is formed by the linkage or network will help us understand the significance of structural diagrams like the one shown in figure 7.6. There are 4 types of patterns which give us a measure of the intensity of regularity of the system from disorder to order. These patterns provide clues on how the system responds to perturbations. The prevailing patterns emerge depending on the food web structure, community composition, networks of competition, and facilitation of the system under study. Here are the 4 types of patterns of networks. We have the planar network. This is a regular network. It is highly ordered, and each node has exactly the same number of links. Under this planar network, we have what we call lattice networks. This can be seen in agricultural fields, schools, herds, and flocks. Planar networks do not offer high connectivity because of the long and circuitous route to reach many nodes. So here are planar networks. Specifically, they are lattice networks. You can see that in the lattice network, each node is connected to the same number of other nodes. Here is a circular lattice, randomized, in which the nodes are connected in an orderly way, but one can go only from this node to that node by going through the other connecting nodes between them. Here is a lattice network exemplified by an agricultural field. Note that if you want to go from this node to the node there, you will have to follow the paths. You cannot go there directly, but you will have to go through each of these until you get to that node. Now, here are random network patterns. In A, there is 30% connectivity. This was determined by counting the number of lines or connections between nodes and the number of missing links. Here is another random network pattern where the connectivity is 100% because this node here has a connection right here. This node here has another connection right there. So each of them have their own connections to each other. And this type of a random network pattern describes a clique. This random network pattern, the third one here, shows that links exist between some of the nodes, but there are some nodes that are not connected to those that are farthest. Connection is only present between two nodes that are close together. Now we go to scale-free networks. This one was random networks, and this one now dwells on scale-free networks. In scale-free networks, the degree of distribution is defined by a so-called power law distribution, where most nodes have relatively few links, but a few nodes, called hubs, have a high number of links. The contribution of the hubs to the overall connectivity is very high. The existence of scale-free networks is explained by two main reasons. They are there in order to assure growth of the system and because of preferential attachment of some hubs to other hubs in the system. From a conservative standpoint, the ideal habitat network is a scale-free network with several large hubs connected to multiple smaller patches. Example, we have Shumart as a large hub in select cities with multiple smaller patches like Alphamart, Save More, etc. Here is a diagrammatic representation of scale-free networks. These are the major hubs linked to smaller hubs around them. Now we dwell on the small world network where most nodes are not neighbors to one another, but most nodes can be reached from every other node via small number of links. Example would be the cell phone, the internet, as exemplified in our very own town. So we have the cable network, which is a smaller node, and this would have a number of links. We are not neighbors in close proximity to those who use the internet in San Pablo, but because of the cable network, we are able to connect. Why are complex adaptive systems more appropriate to the study of ecosystems as compared to linear reductive methods. The reasons would be because the complex adaptive systems do not result in predictive outcomes. They are not proportionate to the output, meaning the outcome is not proportionate to the output. And the output can change abruptly. They produce emergent properties. Let's go now to ecosystem signatures and complexity. When it comes to the temporal aspect of an ecosystem signature, we have these. We could see that in a simple system that is ordered, the fluctuation, okay, is regular, like so. But when it becomes complex and the components are randomly distributed, the vacillation is not so regular. And when it is a simple disordered one, then you have this. The signature at the spatial level is shown to be like so in the simple, like so in the complex, and like so in the simple disordered. In the complex, you have here a random distribution of the nodes, and in the complex, it is a hullabaloo of distribution. Now, if we look at the structural signature of the ecosystem, a simple ordered ecosystem would have this structure, with each node having the same number of links with each other. Here is the structure of a complex system where you can find the existence of hubs that are connected with varied numbers of links. And then the signature of a simple disordered one is like so, where there is no pattern of distribution. Which is the ideal ecosystem? Is it the ordered or the disordered ecosystem? Highly ordered or regular and highly disordered or random systems are simple systems. Complex systems are found in the intermediate zone of regularity. They are between the regular and the random. Properties of complex systems are to be found in the middle of two extremes of order, which has a uniform spatial pattern or temporal equilibrium, and disorder, which has random spatial distribution, demonstrating equal distribution between underlying regularity and complex unpredictability, as shown in the next figure. In a system that is in disorder and order, the tendency for these is to develop as to achieve regularity through self-organization. And this regularity exists between the disordered and the ordered ecosystems. So, as shown in this figure, the measure of ecological complexity increases at the y-axis and it increases to the right on the x-axis. So the tendency is for ecological complexity to increase with time, and its regularity tends to go from disorder to order with time. The best or ideal complexity is one that is in the middle of these two extremes. According to Parrott, an ecosystem tends towards greater complexity via the process of self-organization, which draws the system from the two extremes of order and disorder to a state of maximum complexity. The state of maximal complexity is constrained by prevailing physical and environmental conditions. The natural disturbances may cause an ecosystem state to tend towards greater disorder, whereas human intervention in the form of energy input can move the system state to greater order than might be attained naturally. Example of an ordered ecosystem is a cornfield, whereas a recently opened gap in a forest where seeds are randomly distributed and just beginning to germinate is an example of a disordered ecosystem. We must note that an undisturbed ancient tropical rainforest is probably the best example of one of the Earth's most complex ecosystems. Now let's focus our attention on network patterns in response to perturbations. Different network patterns react differently to perturbations. Consider the case in Figure 711. When a disruption is present, the randomly connected network is broken into several pieces. Now, this is not favorable if links represent roads and nodes are cities. In the case of an earthquake, those isolated cities, due to breakage of linkage, would not be able to receive help in terms of medical assistance, for example, or water. No hubs are occurring in a random network. The scale-free network in the second row of the figure would still be connected to one another. If disruption attacks the hubs in a scale-free network, the network would not easily survive the event of disruption. If disruption attacks a hub with many connected nodes to it, the effects would be more severe. Here are examples: random network, accidental node failure. There will still be connections. In a random network, where there is accidental node failure, the failed node can be disconnected from its link to the other nodes. But if you have a scale-free network where there is accidental node failure, those with which nodes are attached to the hub would be affected. In the third case, we have a scale-free network where the affected is a hub. So here is the hub and it is attacked. So what happens to it? The attacked hub will lose its link to the former nodes that were attached to it. That would mean a great disruption because this hub has some things in it that are supporting nodes that are attached to it. Look at the hubs that are going to be affected. Here you have several nodes attached to the attacked hub, and here is the hub now, which is dislocated from its connection with the other nodes. The effect here is going to be more severe. So let's look at the projected chain of events resulting from the destruction of a high-degree node. Destruction of a high-degree node can lead to low species count, and low species count can lead to contamination of waterways and rivers. There's going to be introduction of invasive species in the waterways, leading to a loss of beneficial species. Reduced complexity in the ecosystem may results. Reduced complexity of the ecosystem results in negative impact on economy and health of local communities, the consequence of which could be high food prices that will lead to malnutrition in the community, diarrhea, and infectious diseases. The anthropogenic disturbance could lead to hybrid systems, which is a system that retains some of the original characters as well as novel elements. When larger changes result, then we have a novel system, which comprise of different species, interactions, and functions. Now we are ready to go to the construction of conceptual models of interaction in an ecosystem. There are three levels and scales of interaction in a conceptual model of interactions in ecosystems. This discussion, by the way, prepares you for the construction of your own conceptual framework. Now, there are levels of interactions in an ecosystem. These levels of interaction begin with the lowest level, which is the locally interacting heterogeneous components. Locally interacting heterogeneous components like individual plants, communities of plants, sanctuaries of wildlife, barangay, government, health centers, etc. These are locally interacting. They are heterogeneous. Next to this level is the middle level of emergent higher entities. This middle level of emergent higher entities would include biodiversity, productivity, and resilience. The top level, the third one, is the global entity, where benefits redounding on people would be found, like people's well-being, like economic state, political stability, okay, monetary stability, financial stability. And note that there's going to be a fourth, which is not one of the levels, vertical levels that were explained, but it is a feedback between process occurring at different scales or intensity. So here's a guide to making conceptual level. Number one, you must identify the locally interacting components, which can be habitats, organizations, or governments, or plant communities, etc. Next, identify the higher entities that emerge from the locally interacting components. Place this on the second row. Examples are biodiversity, productivity, and resiliency. Third, the global level. Identify the global level entity that is obtained from the ecosystem. These are the ecosystem services, not only for human community, but also for complex ecosystem as a whole. This includes ecosystem services, which are the supporting, provisioning, regulating, and cultural services, the weather conditions, economy, etc. And then identify also the feedback loops from the higher levels to the lower levels. Now, you must refer to figure 7.16 in your study guide 7 for further guidance to the construction of your model. The double-headed arrows indicate nonlinear interactions between the given elements. The arrows indicate bottoms-up direction. So you must study figure Point 16 very well. Be sure you are able to come up with your own conceptual framework of an ecosystem that is beside your hometown or city. Good luck. This ends this discussion on Study Guide 7.